fluid mechanics.
Okay. So before we continue, let me give you a 2-minute summary of what we've seen so far in these lectures, and then I'll stop to ask if there are questions. Okay. So what have we seen? We've seen that that type 2b theory on AdS5 cross S5 has an interesting density of states. If you plot the entropy versus energy, you get this nice, or more precisely, if you plot 1 over del S by del E versus energy, you get this nice curve corresponding to gravitons, hagedons, small black holes, large black holes. We've seen that this curve implies a phase transition in the partition function as a function of temperature, a sharp phase transition in the large n limit, okay, from the graviton, the phase of free gravitons to the phase of black holes. Okay, we saw that some aspects of this transition could be captured in free Yang-Mills theory, and we saw that it was at least plausible that the transition from gravitons to black holes had the Yang-Mills words to use for that were the deconfinement transition, the transition from glue balls to the quark-gluon plasma. Well, there are no quarks here, so the gluon plasma. Okay? One lesson we got from that study was that black holes, the physics of horizons, appears to map to deconfinement. The deconfined phase. The physics of gluon plasma. Okay, we understood this in some detail in the first 2 lectures. Many aspects of it, which you remember. Okay, and then the last lecture, we went ahead to say that, well, when we've got this deconfined phase, its properties are often hard to calculate from first principles. But merely using general principles of quantum field theories, okay, led us to the conclusion that under certain conditions, the effective dynamics of this deconfined phase was accurately described by a closed set of equations we could write down with a few unknown parameters. Okay, and these equations were fluid dynamics. Okay, and we then used the equations of fluid dynamics to solve for the dissipation-free solutions, at least a large class of, if not all, dissipation-free solutions of this plasma on the sphere. Okay, and use that to predict properties of rotating black holes in large ADS spaces, and we found that most of the times it worked bang on, though there was one worrying disagreement that has still not been cleared up. Okay, and right at the end of the last lecture, I outlined to you a program that one might follow in order to understand why this is true generally from gravitation, from the gravitational point of view, how fluid dynamics might emerge from gravitation. It's a program that has not yet been brought to completion, but I think it's a very interesting program. Okay, so this is what we've talked about so far in these lectures. Let me stop here to ask if there are questions, comments, or skeptical remarks. Please.
Can you just remind me why I just remember that the dependence of partition function on some chemical potential, conjugated electric charges, were undetermined.
Yes.
I mean, can you just
say that statement again? Yes. So the general partition function was a function of temperature, nu i's, these are the chemical potentials conjugate to the 3 SO6 R charges, and omega. Now, conformal invariance determines we're working in a limit of large charge densities. In that limit, the volume of the space is effectively large. We're effectively allowed to use results that follow from extensivity. So log of z must be proportional to the volume. Okay? Then from dimensional analysis, it must also be proportional to t cubed. That would be t to the power d minus 1 in d dimensions. Now, the remaining parameters, the way I've defined these parameters, z here is trace of e to the power minus beta h, beta is 1 over t, plus nu I hi plus omega a n a. HIs are dimensionless charges. You know, eigenvalues are 1, 2, 3. Okay, so so the chemical potentials for that is dimensionless. L is also a dimensionless number. Momentum, which is mass times distance, is dimensionless. The chemical potential for that is dimensionless. So just from dimensional analysis, okay, and the fact that a conformal field theory has no dimensional full numbers, you can't say much about the dependence of log z on these quantities. You might think that it was a completely arbitrary, let's call it some function f of nu I and omega I. Okay, so what I did for you last time is, in the appropriate limit, the limit of large charges, to determine the omega dependence of this function. How did it turn out to be? It turned out the right answer was that h of nu I into 1 over omega 1 squared into 1 over omega 2 squared.
You only require the angular momentum to be large.
Well, I don't require the angular momentum to be large. All that I require is that, for instance, if the whole thing was uncharged, special case of this, I only require the temperature to be large. Omega could be arbitrarily, if omega was 0, this formula is still valid, as is clear. Right? So it's not necessary the angular momentum is large. It's only necessary that you see, what was the condition really was that the mean free path of a fluid, okay, at every point on the sphere was small. Okay, and that's a condition determined by intrinsic. You see, angular momentum is an emergent property of the solution. Okay, but the condition on validity is local. It's on bits of the fluid. So it's not something that knows about what's going on everywhere. Is this clear?
Yes, but I wonder what was the difference between the parameters omega and nu. I mean, you determined the concrete determinants.
Why was I able to determine the dependence on omega and not on nu?
Right, that was clear.
That's the question? Okay, good. It's possible you can do better. It would be very interesting. But basically what I've used is the fact that we expect in this limit local equations on the S3. Okay? But there's no sense in which we expect some local equations on the S5. I mean, there's no sense that I know of in which, in field theory, you should think of a fluid living on S3 times S5. If there was, and perhaps there is, that would be fantastic. Maybe you can do better than this. Just an observation, the dependence on nu is much more complicated than the dependence on omega, though maybe I haven't found the right limit. Maybe there's some limit in which, that would be fascinating. But I don't know of a way of implementing that yet. The key point was that the S3 was the base manifold for a quantum field theory. S5 was not. That's the difference. Okay, good. Other questions or comments? Okay, fine. So now let's move on. So in this lecture, I'm going to move. So far, we've been dealing with the simplest and best understood situation of ADS-CFT, the duality between Yang-Mills theory and S3 times R times time, and ADS5 and the global ADS5 process 5. Okay, I'm now going to move on to studying a less well understood and less well controlled example of ADS-CFT. Well, it's reasonably well understood, but less special and unique and beautiful and so on. Okay, in order to try to get more interesting phenomena. Okay, so typically well, I don't know what your attitude to physics is, but there are two attitudes you could have. One attitude is that you take the simplest problem and solve it completely, because that will teach you how to move forward in more complicated situations. But sometimes it's useful to go to more complicated scenarios just to see the interesting phenomena, which will motivate you to study the whole area more closely. So that's sort of the spirit in which we should take this analysis. Please.
Just one small question. We saw that with all the 6 charges turned on.
Yes.
Things were not giving you the right answer. Is there any way the calculation is different when all the six charges are turned on except?
Okay, so the question is that in this particular case of ADS5 cross S5, if all 6 charges were turned on the black hole, we got a deviation between the formulas of fluid dynamics and the formulas of black hole thermodynamics of black hole stress tensor at first order in the derivative expansion. Well, of course, in the black hole answer, what we do is just take the answer, expand it in something, and interpret something as a first order in the derivative. Now, from the point of view of fluid mechanics, the calculation was identical in these situations. Indeed, something I should emphasize is that this deviation seems to go away if you turn on any one of these 6 charges. Okay, if you take H1 and H2 not 0, but H3 equals 0, the deviation seems to go away. It's really odd. It's the kind of thing that suggests that some sort of epsilon symbol appearing somewhere, Chern-Simons term that's been forgotten, or something like that. But I just don't have the resolution. Okay, I don't know what's going on, but I think it's an important and interesting point, basically because it seems to, because presuming ADS-CFT is correct, which is manifest, the field theory calculation makes no assumptions as far as I can see. Okay, so it's an important point to clear up for that reason. It's something quite basic. Okay, but I don't know what's going on. Okay, other questions or comments? Okay, good. So let's move on. So let me introduce first the setting in which we're going to be working in today's lecture, and tell you why it's interesting. And soon we'll see why it's interesting. Okay, so the setting is one that Professor Kutasov spent a lot of time explaining to you. Okay, it's Witten's background for confining gauge theories. Now, I think David said dealt largely with with confining backgrounds dual to gravitational backgrounds dual to 4-dimensional gauge theories. Okay, for the purposes of my talk, I'm going to, just because we could do that, but it's going to be a little simpler for me to deal with confining backgrounds due to 3-dimensional gauge theories. This background's simpler than the 4-dimensional one because it's just a Shirk-Schwartz reduction of ADS5 cross S5 itself. This is something that's familiar to all of us. So let me describe the setup very quickly before we proceed. So what's the setup? The setup is, in field theory, consider n equals 4 angle theory on R2 times S1 times time. Now we've got an S1 in the game. It's got a non-contractible cycle. So I have to tell you what the boundary conditions for fermions are as you go around the cycle. Okay? And I specify the boundary conditions for fermions to be antiperiodic. Okay, antiperiodic boundary conditions for fermions are often referred to the situation of Shirk-Schwartz fermions, this Shirk-Schwartz compactification of this quantum field theory. Notice that these boundary conditions break supersymmetry because bosons necessarily have periodic boundary conditions, but the fermions are antiperiodic. So the spectrum of fermions and bosons is not the same in the theory anymore.
Very close to the thermal n equals 4. Just a quick rotation of one space like you mentioned with time.
Absolutely. It's very close to, it's just, in fact, in Euclidean space, it's words whether you call it thermal or Shirk-Schwartz, as we will see. It's just the interpretations that will be different. Okay, so now, but let's think of this as space for a while. Okay, so now we can ask, what is the long distance physics that we get from this theory? So by long distances, I mean long distances on the scale r. I go to a distance that's much larger than r. What is the long distance physics of this theory? Well, clearly it's some 2 plus 1 dimensional theory. What 2 plus 1 dimensional theory is it? Well, let's see what the massless fields in the theory will be. The fermions are not massless because they've explicitly got masses because of the Shirk-Schwartz boundary conditions. Okay? And now the bosons in the theory that also exist in n equals 4 Yang-Mills theory are also not masses. You can explicitly calculate them, the contribution to the masses for these bosons at one loop. This is like the thermal mass of the of bosons. It's a standard calculation. You see that they get masses. Okay, so it would appear that the only massless fields in the theory are the pure gauge fields. So you might think that this theory at long distances is a pure Yang-Mills theory. Now, let's make that statement a little more precise. When do we expect it to be genuinely pure 2 plus 1 dimensional Yang-Mills theory? Well, 2 plus 1 dimensional Yang-Mills theory has a mass scale in it. This is a mass scale that's much less subtle than the mass scale in 3 plus 1 dimensional Yang-Mills theory that comes from quantum effects, renormalization, and all of that. This mass scale is just the mass scale of the coupling constant, which classically has a dimension. Okay, lambda 3, okay, which you would get by dimensional reduction of this theory as lambda for the genuine closed coupling of n equals 4 divided by r, has dimensions mass. Okay, so clearly this theory looks like a 2 plus 1 dimensional gauge theory only, and distance is large compared to r. So in order for the statement in order for this statement to be meaningful, that this theory is really pure Yang-Mills theory in 2 plus 1 dimensions, there must be a separation of scales between the intrinsic mass scale of 2 plus 1 dimensional Yang-Mills theory, that's lambda 3, and the scale of new physics, the scale at which we've got new stuff that starts deviating from the physics of 2 plus 1 dimensional Yang-Mills theory. What scale does this new physics come in? Clearly 1 over r. Okay, so when lambda 3, which is lambda 4 by r, is much, much less than 1 by r, okay, then there's the scale separation. Then we've got new physics, 2 plus 1 Yang-Mills, big separation. Okay, but in this condition r cancels, so it requires that lambda 4 is much, much less than 1. Okay, so in this setup, if you take this Shirk-Schwarz compactified 2 plus n equals 4 Yang-Mills theory and do it at lambda 4 much, much less than 1, this is a good way of producing a genuine, presumably a genuine 2 plus 1 dimensional Yang-Mills theory. However, of course, as you'll see, we're going to be using ADS-CFT in these lectures. And ADS-CFT, while in principle is valid at all values of lambda and n, in practice, if we want to use gravity, can only be used at large values of lambda 4. Okay, so this is when we get pure Yang-Mills. On the other hand, the gravity description that I'll be telling you about in a minute, I won't be telling you about in detail because Professor Kutasov told you about it in great detail, but the gravity is good when lambda 4 is much, much greater than 1. So we've got this usual situation where if you want to get results for a confining gauge theory with a single scale, it's impossible to do that in the gravity approximation. There's a very general reason for that maybe is worth reviewing. The general reason for this is that if you've got a gauge theory with just a single scale, like QCD, then that scale sets the masses of all glue balls in the theory. Okay, so all glue balls of all spins in ordinary QCD, out of the lightest glue ball of every spin in ordinary QCD has a mass of order lambda QCD, because there's just no other number that could enter the game. It could be 5 times lambda QCD or 7 times lambda QCD. Okay, so for instance, the mass of a glue ball of spin 3 is not very, the mass of the lightest glue ball of spin 3 is not very different from the mass of the lightest glue ball of spin 2. However, in a gravity description of this theory, by definition of being a gravity description, there's a hierarchy in scales between the excitations of particles that have spin 2 and lower and the excitations of the spin 3 guys. So there's a hierarchy in scales between glue balls in the gravity description of spin 2 and lower and glue balls of spin 3, which will never happen in a theory with single scale. Okay, so quite, we shouldn't be surprised that every time we try to find a gravity description of a theory like QCD, a confining theory with a single length scale, we'll never manage. It will never work. You know, gravity will not describe QCD. String theory will, not gravity. Okay, fine. So this sounds disappointing to start with, but anyway, we're going to ignore it and go ahead. We're going to say that we're going to study this theory when lambda 4 is much, much greater than 1. This is the regime in which we're going to study it. We're not going to study it because it's a good approximation to 2 plus 1 dimensional pure Yang-Mills theory, because it's not. But we're going to study it because it's some presumably confining 2 plus 1 dimensional Yang-Mills theory. Well, it is a confining 2 plus 1 dimensional Yang-Mills theory. It is a confining theory. We can solve for the mass gap theory. Okay, and we're trying to understand its physics. And the physics is the physics of some confining gauge theory, and so may be interesting. Okay, so that's the attitude we're going to take. You see, this is already less satisfying than looking at n equals 4 Yang-Mills, where you know what the field theory is, you know what the gravity is, so much nicer. But anyway, let's move on. Okay, questions or comments about the setup and the motivation? Okay, part of the reason we're doing this is that this theory has this new additional feature of confinement, which is nice, which was absent in n equals 4 Yang-Mills. We want to see what new physics we get from that. Okay, good. So the next question we're going to ask is, what is the thermodynamics of this theory? I'm going to very briefly, very quickly tell you about this. Again, you've heard of this from Professor Kutasov, but just to remind you. Okay, in order to compute the thermodynamics of the system, the way you do it, well, the way we've been doing it so far, so the way everyone does it, is by taking the theory, going to Euclidean space, and compactifying time on a circle whose size is the inverse temperature. Okay? Let's implement that procedure in gravity. So we've got this theory which was on R2 times S1. There was also time, but now time has also become a circle. Okay. So let's say that this circle is of size R, and this circle is of size beta, where beta is the inverse temperature. Remember that thermal physics instructs you to give antiperiodic boundary conditions to the fermions in the circle. So both these S1s have antiperiodic boundary conditions for fermions. Okay, now we could ask, are there any gravity solutions? Are there any solutions of Euclidean gravity that approach ADS compactified on S1 times S1 times R2 at infinity? Okay? Now, there's one solution. Okay, so actually, before we actually put this theory at finite temperature, I should back up for a minute and say, suppose this temperature has gone to. Sorry, I should have backed up for a minute and just asked about the vacuum of the theory before going to finite temperature. So let me go back to this being time. Okay, and ask, is there a nice solution of Einstein's equations that has the appropriate asymptotics? Your instinct might be to say, well, take AdS5 cross S5 and compactify an S1's direction. Your instinct might be to say, well, take the metric ds squared, which is dz squared plus d, let's single out the one direction that's going to be compactified, let's call that x, plus the other things, minus dt squared plus dxi squared, I is equal to 1 to 2 by z squared, and simply declare that x is periodic. X is equal to x plus 2 pi r. Okay? This is not a good thing to do. This is not a good thing to do. Can somebody tell me why?
Singular.
It's singular. It's singular at the point z equals infinity, at the horizon. You see, what the space looks like, it's got a circle that's very big at the boundary, but then it starts shrinking down to very small, arbitrarily small size as you go to the horizon. Okay? So it's got a singularity at the horizon. Okay? And while we don't quite know the rules of gravity, we should be wary of singularities, wary about treating solutions of Einstein's equations that are singularities as legitimate solutions. So this is not manifestly a good thing to do, please.
So, I mean, in n equals 4, when you go to finite temperature, you do that and you get what you call thermal ADS.
Yes.
This must be a geometry which is closely related to that. But
This must be, well, you don't do quite this. You do what I'm going to tell you about in a moment. So thermal ADS is not quite this. Hang on for a minute. Okay, thermal ADS is the finite temperature black hole, the finite temperature black brane.
Yes.
Yeah, and that is what's non-singular. So that's going to be the solution. Right. So this is not a good thing to do. Okay. However, is there a good thing to do? Well, Nick has told us the answer. We know of a solution of Einstein's equations that is smooth in Euclidean space. That solution was just pretend that the circle was the time direction and write down the black brane metric with the appropriate temperature. Okay, you've seen this metric many times. I'm not even going to bother to write it down for you. But the black brane metric with this temperature explicitly has the property that it has the same asymptotics, but is nice and smooth like a cigar once it's capped off nicely and smoothly like a cigar. Is this clear? Okay, you've also seen this before in this course. Okay, great. So this is what the vacuum of the theory looks like. The vacuum of the theory has the circle shrinking off in a nice smooth fashion down here, and then we've got time. Yeah, maybe I won't. If somebody wants me to, I can write down the metric of this space. But you've seen it many times. Mukund has written it down, and Kutasov has written it down.
I think the question I was asking was slightly different. What I was thinking of, I was remembering is the fact that when you have an S3 rather than in the four-dimensional situation, in that situation you're allowed to find a low temperature space that is described by...
Yes. Why is it different, you ask?
Yeah.
Yes. The answer to that question is easy to see once you look at the metric of global ADS.
Yeah.
When you look,
coordinates on ADS.
that's right. It's a different identification. So if you write down ds squared is equal to cosh minus cosh squared dt squared plus sinh squared. Okay, so let's go to Euclidean space. Plus cosh plus sinh squared d omega 3 squared plus rho d rho squared. Now you see that when you make the time circle periodic, it nowhere shrinks to 0.
Yeah, right.
So there's no singularity. So this identification is completely fine and smooth, but that one is not. Okay, good question. Other questions, comments? Please.
What would you do if the fermions were periodic?
What would I do if the fermions were periodic? Okay, if the fermions are periodic, actually, this thing is probably a good solution, as you would see by T-dualizing. You see, you could what's actually going wrong here? The circle's becoming very small. Now, small circles in string theory are not necessarily a problem. Okay? But small circles with anti-periodic boundary conditions are. They are a problem because if you have a string winding around this, it at some point becomes tachyonic. Okay? However, if you had periodic boundary conditions, you can explicitly understand what's going on. Okay? You can explicitly understand what's going on by T-dualizing. Okay, then the circle becomes very big in some other description. Everything continues to be very smooth. This has been worked out in detail in the context of the D1 brane metric in this paper on Gregory-Laflamme transitions at Yang-Mills. And there I know that this answer is correct. I'm pretty sure it would continue to be true here. Okay, so this would continue to be singular in gravity, but it's not a singular solution in string theory. However, with the anti-periodic boundary conditions, I think it's just genuinely singular. Or by singular, I mean at least unstable. Maybe a solution, but it's not a stable solution. Good question. Other questions, comments? Okay, very good. So that's what the vacuum of the theory looks like. Okay, now how about the thermodynamics of the theory? So now we really have to go back to what we were doing before. We have R2 times S1 times S1, which is of size R, times S1, which is of size beta. Can we think of any manifolds that have these asymptotics? Well, there are two things you could do. There's one thing that's obvious, and once you've written down the obvious thing, there's another thing that's obvious. Okay? The obvious thing is just take this vacuum and compactify now the additional time coordinate. You might ask, just take that solution, the solution that corresponds to this guy, and compactify the additional time coordinate in Euclidean space. You might think, oh my, aren't we going to run into the same problem we had before? But we don't. Why don't we? You see, this capping off of the space happens at the horizon. and at any finite value of the circle, the horizon occurs higher than or before the warp factor behind the other x directions goes to 0. Is this clear? So if you just took this metric and compactified it in an initial direction, you get a space that you could schematically draw as follows. This part is a cylinder, this part has a circle which is non-contractible. Is this clear? Okay, so this was the space circle and this was time. Okay, but now that you've done this, there's something else you could do, obviously, because this problem has a symmetry. There's a symmetry of the interchange between the two circles. So there's another manifold you can write down just by relabeling what you call what, more or less, which looks like this, where this is space and this is time. So we have at least two non-singular Euclidean manifolds that contribute to our partition function. Actually, you have more. You have an infinite number, which corresponds to the fact that you can, really what you've got is a torus at infinity, and you're choosing a cycle to make contractible. We've chosen either the 1, 0 or the 0, 1 cycle, but you could choose any nm cycle. There's some, you have to ensure that that fermions continue to be anti-periodic around it, so there's some integrality properties and so on. However, it turns out that those other manifolds never dominate the path integral. Okay, so they're irrelevant for our purposes. So let's forget them for now. Is this clear? Okay, good. So these are the two solutions that compete for dominating the path integral. Which one wins? Well, you see, the only thing that distinguishes these two solutions in Euclidean space is the size of the circles. Okay, so when the sizes become equal, these two geometries have to have the same Euclidean action, so the same free energy. So it seems very plausible that which one has lower free energy will cross as you go through equal size. Okay, and you can work this out in detail. Well, you can work this out in detail, and the answer is this guy wins at low temperature. If it wins anywhere, it should win at low temperature because it's a vacuum. This is when beta is greater than 2 pi r. And this guy wins at high temperature. Okay, and you have a sharp first order phase transition between these two systems at beta equals 2 pi r. Okay, let's look at the physical interpretation of this system. What was this? This solution was just time period compactified about the original vacuum. So it's a gas of gravitons around your original vacuum. In gauge theory language, it would be called a gas of glue balls. It's the confined phase. What about this guy? This guy has a horizon. It's a black hole. If you took this theory and continued now to Minkowski space, this solution would have a horizon, but this one does not. Is this clear? Because time has become contractible in Euclidean space. Continuing that to Minkowski space gives you a genuine horizon. So this solution is a black brain filling all of your space. This solution corresponds to the quark-gluon plasma, the gluon plasma, no quarks, the gluon plasma. Okay, this is deconfined. You can see this is deconfined also by just computing the Polyakov loop. It's clearly non-zero in this background because it can shrink here. It's clearly 0 in this background because there's nowhere to shrink. Okay, so this transition that we see in gravity is the analog of the confinement-deconfinement transition. Any questions or comments about this? Okay, there's one more thing I want to say before we start getting to, this is all background, but it's necessary background. There's one more thing I want to say before we start getting to the new and interesting stuff. And that's this. Suppose now we plotted the free energy, of the two phases as a function of temperature. Okay. Well, we could do that. We know that these curves cross at r 2 pi r at beta is equal to 2 pi r. Now, the way a field theorist would measure free energy is to say, well, my vacuum has 0 energy. At order n squared, the energy and entropy of the glue of the graviton gas is 0. So let me normalize my energies and free energies to give the value 0 to the low temperature phase. Okay? Of course, this normalization is only accurate to order n squared, but at order n squared, it's a perfectly sensible, legitimate thing to do. So the question I'm going to ask is, how does the free energy of the high temperature phase, look like as a function of temperature? And the answer is that the free energy, that it goes like this. At t equals, t equals beta equals 1 over 2 pi r. The free energy crosses 0. It's above 0 at low temperatures, below 0 at high temperatures. That's why it's the dominant phase at higher temperatures than this, and the subdominant phase at lower temperatures than this. Okay, good. Actually, it's easy to write down formulas, explicit formulas for what this free energy is. It's some number times t to the 4 minus a constant. Okay? And this has a minus sign, so this has a plus sign. How do we know that? Because the formula is just the same as the thermodynamics of a compactified black brane in n equals 4 Yang-Mills theory, because that's what the solution is. Okay? And we know the answer to that goes like t to the 4. Okay? The constant comes from our strange normalization by choosing the 0 of free energies and energies to be that of this other solution, not the natural 0 in ADS 5. Okay? Now, it's an interesting, familiar but nonetheless interesting fact in thermodynamics that the pressure of a substance, okay, of a substance like this, one that has no conserved charges other than energy, is simply the negative of its free energy density. So if we plotted the pressure of this deconfined phase as a function of temperature, we just get the negative of this plot. We go like this. The pressure is positive at temperatures larger than the confinement temperature, and is negative at temperatures lower than the deconfinement temperature. Is this clear? This is the crucial property of this deconfined plasma that differs from the plasma of n equals 4 Yang-Mills theory. The plasma of n equals 4 Yang-Mills theory is like a photon gas. It's always got a positive pressure. You put a lump of it somewhere, it always expands. This plasma behaves very different. At high enough temperatures, behaves the same way. It's got positive pressure, you put it somewhere, it expands. However, at low temperatures, it starts behaving like a rubber band. Okay? It's got negative pressure, like a rubber band does. It's got tension. Okay? You try to put it at low temperatures, it won't expand, it'll collapse. What's going on intuitively, of course, is confinement. You see, when you try to separate gluons very far away from each other, they're connected by these confining strings, which tend to pull them back into each other. That's why I'm making this whole thing like a rubber band. Okay? So this is a crucial physical difference in the property of this plasma compared to the property of the plasma of n equals 4 Yang-Mills theory. And in the remaining half an hour that we have for these lectures, we're going to try to explore what consequences this difference has. Okay. We're going to have to also speed up. I'm going to basically, give you no derivations, just give you results. And the purpose of this lecture, at least this last half an hour, is to have some fun. Okay. You see, the basic question we're going to ask is something like this. Suppose you take a lump of this plasma, it's got finite energy, and you let it go. What's it going to do? Okay. Yes. You might think that if it initially starts at high temperature, it's going to expand, but then eventually it reaches, as it expands, it cools. It goes to low temperature. Eventually it reaches this point where pressure becomes negative. Now what? Well, the answer to this question in an experiment like Rick is that what happens is that it bursts into this bubble of singlets. This deconfinement happens all at once. As I will show you by the end of this talk, this cannot happen in this system. There's a simple large N counting that shows you that this cannot happen. I'll show this to you soon. The rate of hadronization of this stuff is very slow. It's suppressed by order 1 over n squared. Okay, so what could happen? Well, so this thing is going to expand, the pressure goes negative, so it wants to contract. So what must happen, you would think, is somehow you get a static, finite ball of this stuff. Okay, it's this idea that I'm going to explore in many different ways now. Okay, so, to start this explanation, so it's simplest. Okay, the interesting and different thing about the static finite ball as compared to everything else we've talked about so far is the boundary of this ball. Okay, so this is the first thing I'm going to try to understand. I'm going to try to understand this from the point of view of gravity. Since I want to understand the boundary, I want to go to the simplest configuration of this sort, which has a boundary. The simplest configuration you should think of as the infinite size limit of such a ball, which is just a domain wall. It's a domain wall in space in which over half of space you have the plasma, and over the other half of space you have vacuum. Okay? All these intuitive arguments have suggested to us that there should exist a solution in gravity that looks like this. Okay? A solution in which you've got a brane over half of space and nothing over the other half. Question, does there exist such a solution? Okay, well, without doing any work, we can see that if such a solution exists, it has to exist at a very particular temperature. And you can get that temperature by doing a force balance on a pillbox. Suppose we equate x forces. The force here is 0, because we've chosen the normalization of pressure so that the confining phase has zero pressure. Whereas the force here is the pressure of the high temperature stuff. These are the only x forces in the game. So forces can only balance if the pressure of this stuff is 0. So if such a configuration exists, it has to exist only with a brane at the deconfinement temperature. This is an intuitive field theory argument, but it's also a gravity argument because conservation of the field theory stress tensor is an automatic consequence of gravity. It follows from the Einstein constraint equation near the boundary. Okay, so such a solution cannot exist. You can just prove that unless this brane is at the deconfinement temperature. Now, at the deconfinement temperature, such a solution does exist. How do I know it does exist? I know it because my collaborator Toby Wiseman has numerically constructed this solution. Okay, I won't at all take you through many of the details of the solution, except for the two conceptual parts that will be important for the rest of this talk. Okay, so let's try to look at what the solution would look like in Euclidean space. We could work in either Euclidean or Minkowski, but let's first ask in Euclidean space, what does the solution look like? You see, on this side, what do we have? We've got space and time. On this side, we've got space contractible, space non-contractible, time contractible. Okay, this is the plasma. On this side, we've got space contractible and time non-contractible. Okay, this is the domain wall between the two. So now we're saying that there exists a solution that interpolates between these two. Something pretty special must happen at the interpolation line. At this point, both the time circle and the space circle have to go contractible. How many dimensions are we in? Well, of course, we're in 5 dimensions totally, but there are only 4 dimensions that are important to us. The 4 dimensions are the dimensions of the 2 circles, then this dimension in which things vary in field theory, x, and the radius. Everything is translationally invariant in that other 5th dimension. We can forget about it. So so you might worry about whether it's possible, just topologically, whether it's possible from general grounds for two circles to shrink simultaneously at a point. But of course it is, because we're in 4 dimensions, and you have a simple example of such a phenomenon, just R4 in double polar coordinates. At the origin of R4, when you write that in double polar coordinates, each of the S1s of the 2 polar coordinates shrinks. This is manifestly a smooth space, because R4 is smooth. So it's possible for something like this to happen, and indeed that's how the solution does it. In the neighborhood of this domain wall, both these circles shrink at the same point, and where they shrink, the manifold looks is basically R4 in double polar coordinates. Okay? So the thing I want there are many things we could discuss about the solution, but we don't have the time for all of that. So I want you to take away this fact that there exists such a solution of interpolation between. Okay, the other thing I should say is that once you go far away, and by how far meaning far compared to the mass gap of the theory, 1 over r. Okay, once you go far away from this domain wall, this solution becomes indistinguishable from the black brane on the left and indistinguishable from the vacuum on the right. The fall off is exponential. It's exponential because this theory has a mass gap. Is this clear? So we have a gravity solution for this domain wall that interpolates between having a plasma and having nothing, having the vacuum. Any questions or comments about this? Okay, the other thing I should say is that you can, if you wanted, take the solution and compute the surface tension of this domain wall, and you get an answer that's proportional to n squared and is a positive number. That's positive is important. It would have been unstable if it was negative. It's a positive number proportional to n squared. Okay, these are the only things I want you to know about that are important for what I'm going to be saying for the rest of the 25 minutes about the solution. Any questions or comments about this before we now start using this? Okay, good. So now that we've got this solution, we know that it's possible for gravity to have this smooth interpolation between having plasma and not. Okay? Now we're going to ask, what is the effective fluid dynamic description of the fluid in this substance? Of course, in the bulk, we have the same fluid dynamic description that I talked about yesterday. It's given by the Navier-Stokes equations. Okay? But, you see, I'm not going to be satisfied with solutions in which all variations are slow. I want to include solutions in which variations are fast, but only when they well approximate the domain wall. Okay? So, it's not difficult. Okay, so just like we did yesterday, you could write down the most general expansion of the stress tensor, including now as coordinates, not just velocities and temperatures and so on, but also the shape of the domain wall, and expand this most general stress tensor in the derivative expansion. Okay? To a particular order at which we work, all parameters of this expansion can be read off from our gravity solution. So we know the equation of state explicitly, we know the parameters of this expansion explicitly, so we include basically the surface tension term in this expansion. Okay? So the new element is that we'll look at solutions of fluid dynamics which are allowed to have boundaries, and there are extra terms corresponding to these boundaries in the equations of the stress tensor of fluid dynamics. The extra term effectively captures the surface tension of this boundary. Is this point clear? Now, with these new equations of fluid dynamics, we can start searching for solutions. Once again, I'm going to search for dissipation-free solutions. Okay? Let's see what we find. Okay. The simplest solution is just the solution I used to motivate this business. The simplest solution is just the solution I used to motivate this business. It's just a lump of plasma that's sitting there. The temperature of this lump is uniform inside. It's not spinning or anything. It's just sitting. U is 0. It's static. The temperature of this lump is uniform inside here, but is not quite equal to the deconfinement temperature. as you can heuristically see from a force balance. You see, suppose I draw a surface here, the pressure force pushing upwards is to be balanced by the surface tension pulling downwards. Surface tension pulls at 2 points, so 2 times sigma has to be equal to length, so 2r times pressure. Okay, so this fluid sits at a temperature such that the pressure is equal to sigma divided by r. As r goes to infinity, the pressure is equal to 0, and we know that the solution to that equation is at the deconfinement temperature. As when r is large but finite, and you can only trust this when r is large and finite. All length scales have to be large. Okay, when r is large but finite, we're at slightly above the deconfinement temperature. So we're sitting somewhere here at the phase time. Is this clear? Okay, so this is a solution. What does it represent in the field theory? Well, okay, let me tell you about a few more solutions before we try to interpret them. The next thing you can do, while remaining dissipationless, is the analog of what we did on the sphere yesterday. You can take the solution and spin it in a rigid rotation, in a manner that's rigid rotations. Okay? And if you don't spin it very much, nothing terribly exciting happens. You still have this lump of plasma and it's spinning in a rigidly rotating way. Now, of course, it's not true that the temperature and the pressure are uniform in the plasma. They vary, but they vary exactly in the same way that we saw yesterday. The temperature is equal to an integration constant times the local gamma factor, where in this case, because we're in flat space, gamma is even simpler than before. Gamma is equal to 1 over square root of 1 minus omega squared r squared, where r is the distance in polar coordinates from the center. Okay? And once again, though, there is a condition linking omega and the temperature to the size of the circle. It's the condition that's the analog of this. That, you know, when you knew the temperature, you knew what the size of the circle was. Okay? So basically for every omega and temperature, we get one solution. So we get a 2-parameter set of solutions labeled by omega and temperature. R is not a third parameter. It's determined, once you know omega and temperature, by force balance at the boundary, by the satisfaction of the Navier-Stokes equations, including boundary terms at the boundary. Fine, so we've got this nice 2-parameter set of solutions. However, there is a third set of solutions that is a little more interesting than this one. Okay? The third set of solutions looks like this. Instead of having one boundary, it's also rotating in a rigid fashion, but instead of having one boundary, it has two. So it's a ring of fluid, an annulus of fluid that is rotating. This is the third class of solutions to the equations of fluid dynamics in this context. Okay, once again, omega and temperature are the only parameters in the solution. You might think there are two new parameters, R1 and R2, but there are also two new conditions matching, obeying the equations at the two boundaries, and those fix R1 and R2 as function of omega and temperature. So once again, we've got a 2-parameter set of solutions of fluid dynamics, but now these solutions occur with a distinct topology. Let's turn now to a gravitational interpretation of these solutions. What do I mean by an interpretation of these solutions? Well, the first question I'm going to ask, we know that these solutions correspond to black holes. I'm going to ask, what is the horizon topology of these black holes? Okay, so how do I answer that question? Well, I answer that question by looking up here. You remember that everywhere above the horizon of one of these solutions, the space circle is non-contractible. The horizon consists of the field theory directions times that circle, times the Schurz-Schwarz circle. So, if you want the horizon topology in gravity, what you should do is take a circle, fiber it above. Fiber is a fancy, actually may have more, I shouldn't say that, just add a circle above each of these points. It sounds fancy to say fiber it above. I wish I knew what fiber meant. If I did, it would be fiber it above this thing. Okay? And so we're subject to the condition that the circle goes to 0 at the boundary. Why is the circle going to 0 at the boundary? Because the space circle contracts to 0 at the boundary. So the horizon topology is given by a circle above a disk. Okay? It's not quite a direct product because the circle goes to 0 at the boundary. Let's try to understand what that horizon topology is. Suppose the disk wasn't a disk but a line. Just to have the first. Suppose you had a line and you had a circle at above each point in this line, and the circle size went to 0 here. Can you blow this up and see that it's a two-sphere? Okay? In fact, it's the two-sphere written in polar coordinates. Okay? The circle is the phi circle, the line is theta. Okay? I'll leave it as an exercise for you to convince yourself that this is the three-dimensional analog of that. If you have a circle fiber over a disk, subject to the condition that the circle goes to 0 everywhere at the boundary of the disk, that gives you the topology of a three-sphere. Okay? So this solution is a gravity solution with a horizon whose topology is a three-sphere. What about this solution? This solution is different. You see, if we just did the fibering or whatever, the adding of the circle along one of these directions is exactly the exercise we just performed. It's an interval times a circle. But then in addition, we've got an additional circle. That additional circle has nothing to do with the boundary. So that is just a direct product. Okay? So the horizon topology of this solution is S2 times S1. Okay, so let's look, now let's stand back. What do we have? We had a 5-dimensional theory of gravity. And by using fluid mechanics, in this 5-dimensional theory of gravity, we have predicted the existence of black hole solutions of two different topologies, S3 and S2 times S1. Now, had you done this 10 years ago, I don't know, you might have been laughed at, but now since in between 10 years ago and now Harvey Rial came and told us, it wasn't just you, Harvey Rial and his collaborators came and demonstrated to us that there exist in 5-dimensional gravity solutions of whose stationary gravity solutions whose horizon topology is different from S3, in particular as S2 times S1, and these solutions are called black rings. Okay, so these solutions here are the field theory duals, of black rings in Shirk-Schwarz compactified ADS. Okay, please.
Is the temperature constant?
No, the temperature is not constant.
So the temperature on the horizon is not going to be constant?
No, the temperature of the horizon maps to the integration constant of the solution. So while the temperature is not constant, it obeys this equation. And the thermodynamic temperature of the solution just turns out to be this K. So this is the same issue we had yesterday. On the sphere, the local temperature was not constant, but the thermodynamic temperature, of course, was. And that was the temperature that mapped to the temperature of the black hole. Now you might ask, how do you see this more microscopically in gravity? I don't have anything terribly good to say about that. Please.
What if you take your disk and then put multiple holes in it?
Yes, you could do that. You see, fluid dynamics is local. Okay, so if you have a solution and you superpose another solution with no intersection, that will continue to be a solution. Okay, this corresponds to the fact that in this gravity solution theory, we have a mass gap. And all solutions should only be treated as solutions in the approximation of all distances being very large. So if we put another ring here, whether or not there is gravitational interaction between these two, our approximation can't see it. Because the forces die off exponentially, and that will be treated as 0 in our approximation.
I know, but if it's connected, if you take your disk and put two holes in it,
Oh, that doesn't.
you don't see it.
No. The only, as far as we can tell, the only solutions that are dissipation free are solutions with this U1 symmetry. If you can't break that U1 symmetry. Very good. Other questions, comments?
Can you say anything about the stability of the solution?
Okay, we don't yet, that analysis hasn't been done. Okay, it's a very interesting question, and it's answered by an in-principle simple analysis in fluid dynamics. There is a student working on this, but he's been working on it for a long time, so I'm not sure it will ever converge. But it's certainly a doable analysis. Okay, the simplest place, you see, you can take these solutions and take a scaling limit of them. A scaling limit such that you take omega to 0 and r to infinity such that the velocity of this thing remains finite. Yes, so you can get a scaling limit of such a solution in which it becomes like a strip. Okay, that's the simplest place to ask your question. It's the place where the black ring people tell us that the solution should be unstable. Okay, so we should, and there have been suggestions in vaguely similar work in gravity that this instability should map to the Rayleigh instability of droplet formation in fluid dynamics. That may be true. I'm not sure. Okay, but it's certainly an answerable question. But I don't know the answer. I think it's a much easier to answer question than an equivalent question in gravity. Okay, fine. Now, at the equivalent point in my talk last lecture, what I did was say, well, these are the predictions of fluid mechanics. Let's compare with what gravity tells us is the right answer. Unfortunately, we can't do that here because nobody has constructed these black hole solutions. Nobody has constructed these black hole solutions actually in gravity. And that's part of the power of fluid mechanics. It's so much easier to construct these solutions than it is to construct the corresponding black hole solutions. Okay? I want to emphasize, by the way, that this is meant to be a precise construction of the thermodynamics of these solutions in the appropriate limit, the large wavelength limit, just as it was a precise construction yesterday on the sphere. You saw that. It's not an approximation or an intuitive guide to physics, it's correct. Okay, now, since we don't have the relevant black holes and black rings in ADS in this space to compare with, what we could instead compare with, not expecting perfect agreement, but we could instead compare with the phenomenology of black holes and black rings in flat space, just to see if there's any similarity. This is a subject that has been beaten to death. Okay, there are hundreds of papers on this. You look up Harvey's latest review and you'll see all the right graphs there. Okay, so we can do that. Okay, so what do we want to compare in particular? See, just like yesterday, we can take these solutions and compute all their thermodynamic charges. You can compare energies and angular momenta and entropies. Okay, and then in order to compare with the black hole formulas, flat space black hole formulas, what we did is pick a particular energy, it's a typical energy, which one doesn't matter, and plot the entropy versus the energy as the entropy versus energy as a function of entropy versus angular momentum at fixed energy. Okay, and the answer turns out to look sort of as follows. Okay, there are three branches to this graph. This branch refers to rotating disks. Is what the gravity people would call a rotating black hole, horizon topology S3. Okay, these two branches refer to the rings. Okay, these rings, actually there's nothing unsmooth here. Smooth. Okay, there are some details, but basically the important point to note is that while at very small angular momenta there's only one solution, it's the disk. A very large angular momentum, there's only one solution, it's the ring. And intermediate values of angular momentum, okay, you have three solutions, two rings and one disk. Okay, stability analyses have not been done for these solutions, but we expect that with respect to radial perturbations, or with respect to radial fluctuations, the solution here and the solution here are always stable, while the solution here is unstable. Okay, and while fluctuation analyses have not been done, it's easy to compare entropies and check when you get a phase transition. Okay, and somewhere in the middle of this curve, you make a phase transition. At low angular momenta, you're the disk. At high angular momentum, you're the ring. Now, of course, the details of these curves, the shapes of these curves don't match what you get in flat space. Why should it? but the qualitative structure is exactly the same. Is exactly the same as the phenomenology of black holes and black rings in flat space. Okay. Now, whether you should expect that or not, I don't know. But anyway, it's sort of interesting. Okay. So, questions or comments? Okay, so I have 5 minutes to go and I have a lot to say, so let's speed. Okay, the first thing I wanted to say was that you can do the equivalent analysis for Shirk-Schwarz higher ADS spaces Shirk-Schwarz compactified. When you do it in one higher dimension, there's one thing I want to tell you about because it's quite beautiful. When you do it in one higher dimension, the simplest solution is a ball, like a ball that you can imagine in real space, spinning. As you spin it up, something interesting happens. It first starts flattening out, like the Earth does. Okay, then it flattens out so much that it starts dipping. And then this dip becomes so pronounced that it pinches off. And then, instead of looking like a sphere, it looks like a torus. This solution is completely smooth at the level of the equations of, this transition is completely smooth at the level of the equations of fluid dynamics. Though there's a question of validity at this point. But if you ignore that, it's a completely smooth transition. Okay? So, the analog of these annuli and disks are tori and spheres. Once again, you can do the kind of calculation we did to compute the horizon topology of these things, and you'll find S4 for these and S3 times S1 for these. And, well, again, we've not, there's a question of whether these are all the solutions. What I'm presenting to you are certainly solutions. There's a more difficult question of whether these are all the solutions. Okay, that part we've not completely cleared up. But if it's true that these are all the solutions, certainly these are the only ones we managed to find. Okay, then that's a prediction for gravity in Shirk-Schwarz compactified ADS6. You should have stationary black hole solutions with the horizon topology S4, S3 times S1, and nothing else. Perhaps the nothing else is wrong because it's hard to be exhaustive. I mean, maybe if you're the right kind of mathematician, it's easy, but okay, yeah.
Do you mean it's S3 plus 1 after it pinches off or before?
After. So, thank you. Thank you.
Is it clear why you can't have spherical holes inside your sphere?
Okay, that possibility we searched for in great detail, and I think we proved that that doesn't exist. The intuition is as follows. You see, we're in 3 dimensions, so the reason that you're getting things pushed away is centrifugal force. Now, centrifugal force pushes you away from an axis, not from a point. Okay, so when you start hollowing things out, you hollow them about an axis, not about a point. That's my intuition anyway. I think that those other solutions don't exist as a fact, but this is my intuitive explanation. Okay, great. Okay, actually the same logic would lead you to suspect that when you go 1 dimension higher, you should have new kinds of solutions. Because in 4 dimensions, the arbitrary rotation is about 2 axes. So you should have solutions that hollow away from one axis or the other. Okay, and you can then compute the expected topology of these solutions. We haven't done the analysis in 1 dimension higher, but I'm pretty sure that I feel convinced that in one dimension higher we'll get a third kind of topology: S5, S4 times S1, and S3 times S2. Okay, this is all very interesting. Of course, it would be most interesting if you could compare with gravity solutions in this space, which we don't have, unfortunately. Okay, so I have 2 minutes left. So let's forget about these solutions and let's talk a little bit about what we can use them for. Okay, now in all of this we've been doing classical gravity a lot. Okay, but in the end we're interested in quantum gravity. So let's try to do a few thought experiments with these objects and see how they map to thought experiments with black holes or vice versa. Okay, so let's start with black holes. Suppose you're in this space, this Witten space, and you take 2 gravitons and collide them against each other at very high center of mass energies. These are ordinary gravitons, but the center of mass energies is order n square. Okay, what is going to happen? Well, it's hard to be sure, but if you believe that you can model this thing with colliding shock waves, then Giddings and his collaborators, Ealdi, have shown that when these shock waves come near enough, they get enclosed by, trapped surfaces form, and therefore singularities must form. Okay? Presumably the singularities are hidden by a horizon. Okay? Using such arguments, they were able to show that under the intuitive condition, namely when these two shock waves come closer together than the event horizon, the size of the black hole that this energy would form, roughly speaking, they form a black hole. The black hole is this plasma ball, this lump of plasma. Presumably the black hole forms, it sort of sloshes around, equilibrates, and settles down into one of these plasma balls. Very good, one of these black holes. Now, what is the gauge theory interpretation of this? The gravitons were glue balls. The glue balls are sent against each other very fast. At energies of order n squared, you do glue ball collision. What is the result of this? Well, the dominant result is the production, not in this odd theory, of a huge plasma ball. So this is a fantastic prediction. Would have been really fantastic if it was a prediction for QCD. Unfortunately, it's not. But it's a fantastic prediction for this gauge theory, that you take two glue balls, do ultra high energy scattering with them, and what you produce is a plasma ball. This plasma ball is sort of like the fireball at Rick, but with one important difference. It doesn't just keep expanding. It equilibrates and settles down. Now, of course, once it's settled down, what does it do? It can't live there forever. Of course, it decays by hadronization. But how long does it take to decay by hadronization? Okay? You can answer this question by doing some large N counting. Nick, can I have 2 or 3? Sorry. Thank you. Okay, I'll really hurry. Okay. You can answer this question by large N counting. You see, this plasma ball is a huge collection of interacting gluons. What we want to do is to calculate how often these interacting gluons bang against each other and produce a glue ball. Okay. What kind of diagram contributes to this? Well, it's something like this. Some arbitrarily complicated stuff with arbitrarily complicated incoming gluon states and the insertion of one glue ball. Okay, you've got incoming gluons producing glue ball. Okay, now what we're interested in is the net rate of production of these glue balls. So we should take this diagram, square it, and sum over all initial states. But as far as large N counting is concerned, there's an easy way to do that. It's just join this diagram to its mirror image. And sum over all color lines, including those in external lines, because you're summing over all initial states. So we just join this diagram to its mirror image, which is going to be a challenge, but let's do it. Yes, a challenge I failed with, but okay. It's something. The point is that it's some closed Feynman graph for which Toft counting now applies. So let's do the Toft counting to see what the order of n in this diagram is. Of course, we should pick the leading genus. The leading genus is a sphere, so you might think that this is of order n squared. That's right, but not the right physical answer, because we want to add operators normalized such that they produce glue ball states with amplitudes of order 1. Which means we want to add operators normalized such that their 2-point functions are order 1. With the normalization I've used there, the 2-point functions are order 1, are order n squared. As you could check, basically, because the 2-point function would just be this graph. So every insertion point requires an explicit factor of 1 by n. So if you have k insertions in the original graph, that is 2k insertions in this doubled graph, you should subtract 2k. Now k equals 1 is the case of glue ball production. Okay? So what we see here is that the rate of glue ball production in this plasma ball is order 1. So the rate of loss of energy is order 1. The energy of the ball itself was order n squared. Okay? So the time that it takes for this plasma ball to decay by hadronization is a time of order n squared. Okay? So this is very different from what we see at Rick. There's dynamics, there's fluid dynamics that stabilizes it. Then it settles down, and there's a totally different time scale separated by n squared over which hadronization happens. What's the gravitational interpretation of this hadronization? It's really simple. It's Hawking radiation. You see, black holes that are localized somewhere don't live forever. They decay by Hawking radiation. You can easily do the calculation in gravity and check that the rate of Hawking radiation is order 1. The simple way to do that is to note that Hawking radiation is thermal radiation and the temperature is of order 1. Therefore, the rate must be of order 1.
But here you're sure that blue balls should be produced because there are no other particles, but with black holes you're not sure what the remnant is at the end.
Well, the remnant is at the end. Right. But at the moment, I'm not even reaching the end. I've got this big black hole and it's sitting there. As long as you trust Hawking's semi-classical calculation of Hawking radiation, you know that whatever else happens, it Hawking radiates. Okay? So that must have a gauge theory analog, and we've just seen what it is. It's this hadronization process that happens at the rate 1 by n squared. It's not surprising that it's basically thermal because everything is very hot here. Okay, so I just have to stop now. Maybe I'll leave you with one last thought. Okay. It's a thought about very interesting physics about this object. You see, what we've concluded is that a black hole is dual to a lump of the strongly interacting plasma. Now, if you think about this a little bit, you might think this can't be right. It can't be right because black holes don't behave like lumps of gas. In what way don't they behave like lumps of gas? In a very precise way. Suppose you've got a black hole and you send something in it at very high energies. The stuff that you send at it is absorbed in a manner that has an infinite energy limit. Okay? At arbitrarily high energies, things continue to be absorbed in black holes. You would think that lumps of gas are very different. Lumps of this plasma are very different. If you send something at energies much higher than the energy scale in the problem, which is the temperature, which is order 1, it should just blast through. So how can this soft stuff stop it from blasting through? Okay. Apparently, this is wrong in this gauge theory. There's some intuitive, in our paper we suggested an intuitive explanation based on shady arguments and Parton distribution functions, which you can take or leave for why this happens. But it's a very interesting phenomenon. This lump of strongly interacting plasma behaves like a black hole. You send any glue ball through it, no matter how fast, there is a non-zero probability, one you can compute in fact, using gravity, that it will be absorbed. Even in the limit of arbitrarily high energies, of course, energies are lower than n squared, where your gravity approximation is. Okay, so that's all. That's the thought I'll leave you with. The last sentence is that this is actually a situation in gauge theory where you could clearly set up the Hawking information paradox. You see, one of the nice things about this construction is that it's a construction, although in the fluid dynamical limit, of a black hole that is localized. This is the first construction that I've presented to you of such sort, which is very important because such black holes can be created, for instance, by the experiment that we talked about, and then they decay. So this is a situation in which Hawking's information paradox really applies. So it may be a situation in which to analyze it using the gauge gravity duality. Okay, so that's all. That's the end of my lectures. Sorry for going over time, and thank you very much.
Any questions for Shiraz? Comments?
Oh, comment. The topology of the black holes you find is consistent with the black hole topology theorem, which doesn't actually apply in ADS. So
Yes, you're completely right. It's consistent with black hole topology theorems, even though it doesn't apply. Right. So maybe there's a better black hole topology theorem that does apply in ADS.
Any other questions? Okay, well, let's thank Shiraz for a wonderfully clear and fun set of lectures.